Okay, so that should be fine now. All right, sorry. So opening Maestro. So you click on package contents, then I'll bring you to this, go through the contents folder, Mac OS folder, and then click on this weird thing. And then it should open Maestro for you.
Quick one, could you record this?
Yeah.
And is it recording?
Yeah, it should be recording. Yeah. Okay, perfect. Yeah. Okay, so this is kind of what Maestro looks like. It's just, it just contains any structures that you build. It'll contain, inputs for calculations for DFT and for perturbation theory, stuff like that. So the first thing, just to keep organized that you want to do is you're going to want to start a new project. So we could go to File, New Project, and then name it whatever we want. I'll call it Homework 1. Oh, can't do that. Homework 1, 2, 3. And we'll open a new project. So that's all good. And then if we want to start actually building a structure, the first thing we'll do is we'll go to this button, Build. We'll click on it. And then it'll bring up this sub menu. And then from this sub menu, we'll click this button in the top left, and that'll open kind of a new canvas for building a molecule. And then if we want, we can rename it. I'll call it structure 1. Perfect. All right, so now in the structure, so for the homework, the reaction coordinate that we're going to do is using a molybdenum catalyst to do an olefin epoxidation. And so the first, actually pretty much the only molecule I'm going to build for you today is this guy here. So a few things about Maestro. So I've shown you how to kind of create a new entry for a structure. But once you actually start building the molecule, there's several ways that you could approach building a molecule. The most simple, I think, in Maestro is this draw function here in the bottom left. So if we click that, it'll bring up any available atom that you want to build. So for example, if I'm starting with my molybdenum complex, I will click on this button here, and that'll bring up the whole periodic table. And then I'll start with my molybdenum atom. So I'll click on molybdenum, and then I'll just place it anywhere in my canvas like that. And then the nice thing about the draw feature is from that central atom, now I could draw connectivity to that atom to build up the ligand. So in this structure that I'm starting with, it's a molybdenum, and it has an oxo, it has its ch2, and then it has 2 chlorine atoms. So now I'll go ahead and draw those ligands from molybdenum. So let's start with chlorine. It has 2 chlorines. So I'll now click on chlorine, and then I'll click on my molybdenum atom, and then I'll drag away from the atom. And you see there's kind of this yellow line. And then if I release the mouse button, it'll draw my chlorine bound to my molybdenum. Is that better? Maybe. Okay. So now I have molybdenum chlorine. Now I'm going to add in my second chlorine, doing the exact same thing. I'm going to click on molybdenum, drag over, put a chlorine over here. Now I'll go ahead and build my oxo. So I'll click on molybdenum, draw the oxygen over here. Thank you. And then finally, I'll put in what's going to be my ch2 ligand. So now I pretty much have the basis for the system, but notice that when I was trying to draw my oxo, it actually drew a hydroxy. And the reason for that is it'll assume, a single covalent bond, and then it'll fill the valency of whatever atom you place there. So for oxygen to put a hydrogen, for carbon to put 3 hydrogens. If we now want to remove those atoms, there's 2 ways we could approach that. We could either click on this red X here, and that kind of like brings up a little eraser. And then I could click on these hydrogens that I don't want and remove them. Alternatively, what I can do is I could, if I'm not in my draw menu, I could select these 2 atoms that I want to remove. And then this button here does the exact same function. If I click on it, I remove those 2 atoms. So that's kind of the basis of actually building up your molecule, placing the atoms in space such that you could actually go calculate them later. However, there's a few caveats. So I know, because I've designed this homework, that this molecule is actually supposed to be in a tetrahedral geometry. And the way I have it drawn now, it's probably not even remotely close to tetrahedral. It's kind of planar, it's square planar almost. And so a thing that you want to utilize is your chemical intuition. If you know that a system is going to be tetrahedral, you should build the molecule as a tetrahedral and save the computer some time so it doesn't have to do that itself. So let's say that I want to make this tetrahedral. There's a function in Jaguar that's called the move function, where I could select certain atoms, and then if I press Command G, you'll see that it brings up this move atom function. And then if I hold right click, I can move atoms in space manually. I could also rotate them. I don't know what it is for you guys, but for me, if I hold down the middle button, I could rotate certain groups of atoms. So using this function, I'll rotate this CH2 into place, and then I'll translate it to here. How about? And that kind of gives me a better, I'm getting closer to my tetrahedral geometry. And then I could do the same for oxygen. I'll click on it, and then I'll hold right click, and I'll move it over here like that. So now I'll click OK. And now if I kind of look at the overall quality of my molecule, it's a bit closer to tetrahedral, right? It's not perfect. I could probably move the CH2 group further like this, but it's pretty close. Actually, no, it's not pretty close. This is pretty bad. Oh yeah. So another thing we could do is we could also adjust the distances between atoms and the angles. So clearly this molybdenum chlorine bond is probably a little too close. So if I want to change the distance of that bond, I'll simply click on the two atoms, and then I'll right click, and then it brings up this menu. There's a lot of different features. However, for now, we want to just adjust the length. So I'll click on adjust length. And then if I click on this yellow cone here and hold it and drag it, it allows me to change the distance between the two atoms. So molybdenum chlorine, I don't know, maybe like 2 or something. I think that's probably close enough. I could then do the same for the other molybdenum chlorine. I'll drag it, make it 2. Molybdenum oxygen should probably be shorter. And then molybdenum carbon should also probably be shorter. So this is probably good enough. You know, I think DFT can figure it out from here. One more thing, we could also change the angles between atoms. So similar to how you click on 2 atoms to change the bond distance, if I click on 3 atoms, so chlorine, molybdenum, chlorine, and then right click, now I could adjust the angle. So I'll do that. Since this is tetrahedral, I'll set it to 109, how about? Or something close to that. Okay, great. So I will assume for now that this is a good enough geometry input that the calculation should run okay. So we've built the molecule, but now we want to actually go and submit the calculation for geometry optimization. So how do we do that? So there's presets here. You notice there's an optimization, transition state, single point energy. But if you want to access the whole list of available calculations, we go here to tasks. And then this will bring up all the different programs that Maestro is actually built for. So it's not built for just Jaguar. It's built for things called Glide, Desmond. These are like bio programs. But since we're doing Jaguar, we'll go over to Jaguar. These are all the calculations Maestro is able to submit for Jaguar. And so we're going to be doing an optimization calculation. So I'll click on optimization. And that'll bring up this window here. Let me make sure that I'm actually following my own homework. Sure, good enough. So we have this optimization window, and it'll look essentially similar for different types of calculations. But the thing for this homework that we're going to start with is, again, we're going to be using the PBE functional to do a geometry optimization and a frequency calculation for a few molecules. And so I think in this homework, I say, so for the first part, we're going to use the PBE functional with this basis set. It's called, in Jaguar, it's called LAV3P plus star. In lecture, Bill mentioned that for very large atoms, you don't want to explicitly calculate all the core electrons, because that'll take forever, and you have all these weird relativistic effects that can occur for heavy atoms. So what you do is you take those core atoms and you replace all those core atoms with an effective core potential. So this LA, that stands for Los Alamos, they developed a whole suite of pseudopotentials that seem to work pretty well with DFT. So that's what we're going to do, especially in the case of molybdenum. We don't really, it's not that crucial that we use a pseudopotential, but we're just going to do it because we feel like it. So to change the basis set and the DFT functional, there's these two boxes here. If I click on this one, it brings up a whole list of functionals we could use. We'll just search for PBE. There's a whole bunch of variations, but we're just going to stick with PBE for now. So we'll click on that. And then for basis set, I could do the same thing. I click on this box, brings up a whole list of atoms, or sorry, a whole list of basis sets. And I'm going to select what I said, which is the LAV 3P star plus. LAV3 star plus. Here it is. Okay, so that's good. For systems that have charge, we could change the charge. Let's say I wanted to do a -2, I could do that. We could change the spin as well. So let's say if it's a -1 doublet, it'll automatically change the spin to a doublet. Or if I wanted to change it to quartet or whatever I want to do. But for now, in the system, it's going to be a neutral singlet, I think. Yeah, singlet. Okay. So that's kind of like the basics of the calculation. We have all these different tabs that we could look at. So here we could switch between DFT or Hartree-Fock or MP2 perturbation theory. We could treat the SCF program as automatic, or we could select if it's restricted or unrestricted. We could select if we want to do time-dependent DFT. We're not going to do that for now. And then there's other more technical things like the DFT integration grid that we could also modify. This is just simple, inputs for how the SCF is done. So in these calculations, we use the Born-Oppenheimer approximation where we treat nuclear and electronic degrees of freedom separately because the electrons move so fast relative to the nuclei that you're able to actually, decompose those two degrees of freedom and calculate them separately. So how the calculation runs is you'll actually minimize your electron density. And then based on the minimized electron density for a given geometry, you then update the coordinates of the atoms. And then, so you're trying to minimize the forces and the energy. And then once you update the coordinates of the atoms, you do the SCF electronic minimization again, update the coordinates, and then you just keep doing this again and again until both your electronic degrees of freedom and your nuclear degrees of freedom are both minimized. And so SCF just means self-consistent field. Doesn't really mean anything. So we won't change anything here, but eventually if you get into more intricate systems, you'll need to change things like the initial guess for the electronic wave function. You'll change things like the convergence criteria. Sometimes if your wave function has a very small or even like inverse like HOMO-LUMO gap, you'll add like a virtual shift to your LUMO orbitals to kind of solve the wave function more. You'll converge on the wave function more quickly. There's also things like thermal smearing. So like if you assume that your electronic like density of states is not a step function, you could actually add like a little bit of like a Fermi Dirac distribution to it. But for now, we'll just ignore that. And then probably what's most important for you guys is the properties tab. And this is where we could actually select if we want to do things like the vibrational frequency calculation, if we want to calculate the orbitals or surface densities or atomic charges. So for this calculation, I'm going to ask you to do calculate a reaction coordinate. And to do that, you're going to need Gibbs free energies. And to calculate Gibbs free energy, you will have to do vibrational frequencies. So I'll click on this tab, asking it to calculate vibrational frequencies. Within this, you could select how you want your Hessian treated. If you want to calculate IR intensities, you could tell it for the thermochemical properties. If you want to change temperature and pressure, you could do so. But for now, we'll just stick at 1 atmosphere, 298 Kelvin. So. And then finally, we could also like include implicit solvation. So by default, these calculations will just be the molecule in a vacuum. But and a lot of times, in an experiment, you're not working in a vacuum. So we can include what's called an implicit solvent, which is what Bill discussed, where you surround your molecule with this energy surface, And then based on that energy surface, you can calculate like surface tension, cavitation energy, all sorts of properties that might be important to, match experiment. But for now, we'll just do vacuum. Okay, so now our calculation should be good to go. Unfortunately, I can't see the bottom of this window. I don't know about for you guys. Can you see the bottom of the window on yours?
I had to maximize it. And I could,
Oh yeah, is that the move?
oh,
Almost. Okay, watch this. Hey. Quit. If you notice, right here, you can click that button if it shows up on your computer screen. Okay. Well, alternatively, you could click this button and no, that doesn't work either. Okay. So on your, actually, it should be in the homework. Okay. Yes, beautiful. So you'll click on this little drop down arrow here. And if you click it, it should bring up some options. I don't know what they are, or I don't remember what they are, but one of them should say edit. And if you click edit, it should bring up this thing, this text file. And this text file is what is actually your calculation. So Maestro's, remember, is just the GUI, but this is actually your actual Jaguar input file. So notice it just specifies the basis set that we asked for. This line tells it we're doing a geometry optimization. This is telling it that we're using the PBE functional. And then this tells it we're doing a frequency calculation. And then these are the Cartesian coordinates of those atoms. So at this point, we built our molecule, we've selected all of the, different tags that we want for the input calculation. So now we could actually go do the DFT calculation. So let's switch gears and now hop onto the Caltech HPC. So for Mac, you could access it via like the terminal. In Windows, you could do it through PowerShell, or last night I recommended there's a program called MOBA Xterm that you could use, whatever your preference is. So let's go ahead and get that started. So to log into the HPC, we use what's called the SSH client or SSH command. So I'll type SSH and then my username, and your username should just be like your Caltech email. So mine's just Musgrave. And then it'll be at login.hpc.caltech.edu. Now, if I press enter, it'll ask for my password. Again, it should just be the same password as your email. And then it'll bring up this thing. So Caltech HPC uses like dual authentication. So if it's telling me here, do I want it to notify me or do I want to do other options? I just press 1, press enter, and then on my phone, if I open Duo, it should bring up something asking me if I want to log in. I press approve, and then I'm in. And there's a few details that it'll bring up. It's telling you don't do anything illegal. It tells you like how much usage you have on the Caltech HPC this quarter. But the way that you confirm that you're in is it'll show the command line here. So I'm now logged in. So again, you want to stay organized on the Maestro side of things, but you also want to stay organized on the HPC side of things. So I'll start by creating a new directory. The command you use is called make directory, or mkdir, and then you can choose whatever name you want. So I'll do ch121 homework 1 spring 23. Now if I ls, which is list directory, you'll see it shows you all of the contents within your current working directory. So notice I just made this directory ch121 homework 1 spring 33, and notice that directory is here. I just created it. Now, if I want to go into that directory, I do the command cd, which is change directory. So I'll cd and then ch21 homework 1 spring 23. You could also press tab to like autocomplete like that. And then I press enter. Another command that is useful is print working directory, or PWD. That'll tell you in which directory you're in. So if I type PWD and press enter, it's showing me I'm now inside that directory I just created. So we've learned how to navigate a little bit and learned how to create a directory, how to figure out where we are. So now if I actually want to create this input file for this calculation, I'm going to use a command called vim. And essentially this just allows me to read files and create files. So I'm going to be creating this input file for this calculation. So I'll vim, and then the name of the file, I'll call it molybdenum. How about I just call it reactant1, reactant1. And then for Jaguar, the extension is .in for input files. I'll then press enter. And so now I just created this file. It's obviously empty. So now this is where I'm going to like paste the input contents for my Jaguar calculation. So I think that's essentially what I said here. Let me actually get the contents for that file. Okay, so again, vim reactant.in. So now I'm in this blank canvas. If I want to actually insert something, I press I to go into insert mode. And then I could simply copy what I had from the optimization window. So that you know, I could copy this text here, and then I'm going to go ahead and paste this text into my new file just by simply pasting it. For Windows, I think it makes you like right click to paste things. I don't know why, but that's how you do it on Windows. So now I have my actual input file pasted. If I press escape, I will exit insert mode. And when I'm not in insert mode, I could type anything. Oops. I could almost type anything without repercussion. I actually have to go into insert mode by pressing I to be able to type things. Okay, so now we have our input file. I'm going to go ahead and save this file. And to save it, you type :WQ, and then that means to write and then quit. If I press enter, now if I ls in my directory, you see I have just my input file. So that's good. Everything seems to be working. When we submit calculations on the HPC, there's two things. You will have the input for your actual calculation, but you'll also have a submission file that actually submits the calculation to the HPC queue. So here, this is what a Slurm submission file will look like. Slurm is the actual job scheduler. So I'll go ahead and copy and paste this. Okay. Now so I have that copy. So now I'll create a new file, call it slurm sub. I'll go into insert mode and paste that. And now I have my slurm submission script also ready to go. So let's just briefly go through this. So these first lines that all start with sbatch, that's giving the scheduler details to our calculation. So this is telling it we're going to allow the calculation to run for a max wall time of 5 hours. This tells it the number of tasks I'm going to use. Depending on the system, this could mean a lot of different things. But for now, this just means the number of CPU cores. All right, we're going to use 8 of them. This tells you the number of nodes we're going to use. Usually, we're going to be using 1. This tells it the memory per CPU core, so 4 gigs. This is the name of the calculation. And then finally, so if the line starts at the pound, it's commented out unless it's an sbatch line. So these lines are all commented out. They're useless. And then finally, this last line is the actual execution of the Jaguar program to run the calculation. So this is where the Jaguar executable is located. It's telling it to run Jaguar in parallel with 8 cores. And then the only thing we need to change is the name of the input file. So I'll change this to reactant.in. I could go ahead and save that. Now, if I ls, I have my reactant.in file, and I have the slurm submission script. And now to actually submit this calculation, we're going to use a command called sbatch. Oh, in the homework, I called it jaguar.sub, whatever. So to actually submit the calculation, we'll use the command sbatch, and then we'll reference whatever the name of our submission script is. So jaguar.sub. Now, if I press enter, it should tell me that my job was submitted and this is the job ID. So now I could actually check the status of my job using this command sq. So if I type sq, oops, and then -u, and then my username, which is Musgrave, it'll show me all the calculations that I have running. And notice here at the top, this is the calculation I just submitted. Notice again, it has the job ID number, the name of the job, and then this tells it the status. So PD stands for pending. That means it hasn't actually started running yet. It's in the queue to start running. R means that the calculation is running. If it has R, it'll also show you the time. So these have been running for a while. And then if it says C, that means that the calculation has completed. So you should be able to go check it. In addition, you could monitor the Jaguar output file as the calculation is running. So let's say, for example, my calculation was running. It is okay. So notice now it's where'd it go? Oh, now it's down here. So now it says it's running. It's been running for 30 seconds. I can monitor the output file of this by vimming into the .out file. So now if I ls, notice that there's reactant.out. I could vim into this file. And then this is the top. I could just scroll down and see all the stuff it's doing. So again, it's telling me my inputs. It's using 8 threads. It's using an effective core potential on 3 atoms. And it has a total of 77 basis functions. And then we could just simply look through this file. It just started, so there's not a lot to it right now. Oh. So now if I look, so this is what like the SEF calculation looks like. These are each of the iterations. This is the electronic energy, and these are things like the change and the density change, the error. It converged, so that's good. And then it prints out all these different energies that I may be interested in. Prints out the HOMO and LUMO energies, all the orbital energies. The output file contains a whole lot of stuff. So it's running very fast because it's a very small calculation. So I'm already actually at geometry optimization step 5. So yeah, so the calculation should run fast. If it's complete, it'll say C. If the calculation completes and then a long period of time passes by, it'll just be removed from your SQ command. So like eventually this will say C, and then it'll just disappear. Eventually when the calculation completes, you can actually, it should look something like this at the end of the file, where it'll say job reactant completed, and then I'll tell you the time and date of when the calculation actually completed. If you don't want to vim into the file and have to scroll all the way to the bottom of the file, another thing you could do is you could just type tail and then the name of the file you want to see the end of. So tail reactant.out will show me the very end of the file at that moment. So great. So my calculation is now complete. Job reactant completed at 2:34. So just now, it just completed. So now if I SQ, oops, it's already gone. Notice that job 1 is not here anymore. Okay, great. So the calculation is done. So now we could actually go through the output. We could vim into the output and kind of look through the file. So let's say I want to see how many optimization steps it required to actually complete the calculation. In Vim, you could search for particular strings. So let's say I want to search for the string end of geometry optimization, or end of geometry optimization. If I type / and then enter the string and then press enter, it will bring me to the first instance of whatever string I desired. If I then press N, which is next, it'll bring me through every instance of that string. So here's end of 2, 3, 4, 5, 6, 7. So it took 7 total optimization steps to get to the minimized geometry. Okay, great. What else can we do? So in this calculation, we did the optimization, but we also did the vibration calculation. So let's take a look at that. That is usually near the end of the file. So if I go to the very end of the file with Shift G, and then scroll up a little bit. Or actually, how about I go to the beginning of the file, and then I look for the string vib. That'll bring me to the top of the vibration table. So one purpose of doing a frequency calculation is you can confirm or deny whether or not your system is actually at a true minima. If you're at a true minima, there should be 0 imaginary frequencies. Every frequency should be positive. If you happen to optimize to some transition state or higher order transition state, you will find that you'll have one negative frequency, or at least one negative frequency. And the vibrations are ordered in ascending value, meaning that your first vibration is the smallest. So notice my vibration 1 is 93. That means that's my smallest frequency. I don't have any that are negative. So that means that I've optimized to a true minima here. So that's good. And these are in inverse centimeters, by the way. So great. So I've optimized my structure to a true minima, and I've checked my frequencies to confirm that. So what else can I do? Well, the frequency calculation also allows me to compute statistical mechanics derived thermochemical properties. So I get 0-point energy, entropy, and then therefore I could get things like free energy and enthalpy. So if I go to the very end of my file, again, Shift G, there's this table here that shows me for 298 Kelvin and 1 atmosphere, it gives me all the mode dependent internal energies, heat capacities, entropies, enthalpies, and free energies. And then it does the work for you and sums up these values to give you the total internal energy, the total enthalpy, and the total Gibbs free energy. So that's fantastic. That's essentially for the homework, you're going to be reporting this value here, which is the total Gibbs free energy. So great. So we know how to look at the frequencies. We know how to get our thermochemical properties. From there, we'll be able to compute our reaction coordinate using those Gibbs free energies. Let's now actually look at the optimized geometry of our system. So the optimized geometry, assuming your optimization completes, will be contained in the .01.in file. So if I vim into reactant.01.in, it looks very, very similar to the input because this file could actually be used to restart a calculation. But these coordinates are now the optimized atomic coordinates. And then anything follow that is actually just like the optimized wave function for this geometry. So if I want to look now at this optimized geometry, I could simply just copy and paste this portion of the file, and then I could put it on my local computer and open it in Maestro. So you could do that using any like safe file transfer protocol, or for me, I'm just gonna vim into a new file on my desktop. So I'll cd to my desktop on my local computer, and I'll vim into reactant.01.in. I'll go into insert mode and I'll paste it. I'll then press escape and then write and quit. So now if I go to my desktop, there's this reactant.01.in file. If I go to Maestro, I can now go to File, and then I can import that structure. I'll go to my desktop, and then open it. And there it is. Beautiful. Whoops. Yeah, that's it. I'll go to ball and stick because it's better. And there's my optimized geometry for the file. So let's just quickly see what changed. So the molybdenum oxygen distance, if I measure it, it's 1.51. In my input, it was 1.78. So it's significantly shorter than I guessed it to be. The molybdenum carbon distance, I can measure that. That's 1.79. In my input, it was 1.79. So I nailed it. God damn. Yeah. So that's analyzing the geometry. It looks like we did pretty good. Additionally, we could actually visualize vibrational data. So to do that, it's not as simple as copying and pasting it onto your desktop because the .vib file, which is where the frequencies are, is very long. Oh, actually, no, it's not. It's sometimes very long. Sometimes it's not. I can copy and paste this. Boom. I'll put it on my desktop. So now on my desktop, I have a .vib. So to import the frequencies or the vibrations, I go to Window, and I click on Project Table. I highlight whatever structure I want to import the frequencies to, and then I click Data, Import Vibrational Data. And then I go find that file. And now notice this little blue box pops up that says V. If I click on that, now I could visualize all the frequencies that I computed. So remember, when I looked at frequency 1, it was 93. Here it is. If I click on animate, it looks like it's just like a chlorine, molybdenum chlorine angle stretch. Increase the speed. Let's look at like something more interesting like this. So here's, I don't know what the heck that is, but you know, pretty wild, right? You can show the arrows just in case you can't see. It's going that way. You crank it. Yeah, okay. Okay, so that is about it for homework 1. Any questions?
As a job, you could just make vibration frequencies and that's doing a frequency calculation.
Yeah, so in Maestro, in the optimization tag, if I simply just click this box, what it actually does is like, remember this is just a GUI, but if you go look at the actual input file, this line here, the I freq equals 1, that tells Jaguar that you're doing the frequency calculation. So if I, for example, deleted this line and then submitted the calculation, it wouldn't do the frequency calculation. But if I have it, it'll do it. Yeah. And then the same thing, if I, for example, remove this line, the I geopt equals 1 line, this would just do a single point calculation. It wouldn't update the geometry of the molecule. It just do the single point, and then it would do frequency calculation. Any more questions?
For the Slurm solution file, is there like an account to go to? Because I don't want to actually go to like my
yeah.
account.
Yeah, so
Like in the example.
yeah, Caltech, that's outlook. So yeah, so in your input file, you need to do a -A option. And then from there, you could select what group you're billing the calculation to.
But, that's what I was wondering, is what's the name for like this class?
Probably, oh, so I think it's just WAG. Should be just WAG, yeah. Let's see, has anyone started doing calculations yet? Excellent work. Who else? Okay. A lot of you are very behind. Does that answer your question? I think you just do S batch -A WAG, yeah. Let's see. If there's no other questions, so the rest of the homework is build these structures in Maestro, and then do the optimization plus frequency calculation for all of these at the PBE level with this basis set. Report the free energies. I just showed you where that is. And then finally, with those free energies, you should be able to compute the reaction coordinate going from this starting molecule plus ethylene to a cyclic molecule, and then you should be also to calculate the energy change from that cyclic molecule to generating propene. And then finally redo everything with B3 lib-D3 and this larger basis set, and then tell me, did it take longer and what do you expect to be more accurate? And that's it. So hopefully that was useful to you, and let me know if you have questions. So the homework's due Thursday at like 11:59 p.m. so midnight. And then we have office hours Wednesday right after class. Does that work for everyone? Does that make sense to people? Okay.
How do you want to-
Yeah, so good question. So you could submit, so you'll submit it on Canvas. I don't have any strict guidelines for formatting, so you could submit it as a Word document or a PowerPoint slide or even Excel sheet, as long as it's legible. That's fine. Or you could, yeah, write it by hand, whatever you guys want. Does that make sense? Okay, all right. Good job, everyone.